As we saw in the last lesson, we can solve trigonometric equations. Now, the first part of lesson 19 involved solving what we call linear trig equations, and this part is going to look at quadratic trig equations. So, a trig equation with 2 as its highest power would be considered quadratic. So, for example, cos squared x equals 1 is a quadratic because we're squaring the cos x, or 2 sine squared x plus 1 equals 1. Again, we got this 2 as an exponent in both of these. Even sine x times cos x is quadratic because you can think about it like it's in factored form, one of the factors being sine x and the other one being cos x. So even though they're not the same, and I can't write it with that exponent 2, it's still quadratic. To solve a quadratic trig equation, we need to factor it and then set each factor equal to 0, just like we're used to doing with polynomials, and then solve each part separately. The solution to the problem is going to be all the individual solutions. So let's start with an easy one that we can use a graph to help us visualize. If we want to solve cos x tan x, that is quadratic. Cos x would be one factor, tan x would be the other factor. Again, we need to know an interval, in this case 0 to 2 pi, because trig functions being periodic, they would have infinite solutions if we didn't specify a period that we're going to solve it on. So we set each factor equal to 0. So if I take cos x and set that equal to 0, I just need to then solve cos x equals 0. And that means that it's easy enough to see this on the graph, so that's why we have the graph here. If I were to look on this graph, when cos x equals 0, that's right on the x-axis. So between 0 and 2 pi, this cos x graph hits y equals 0, or cos x equals 0 twice. Once at pi over 2, that's this one, and then another time at 3 pi over 2. So if you plug in those numbers, pi over 2 or 3 pi over 2 into cos x, it will equal 0. We're also checking to see when tan x equals 0. That's our other factor. Again, that just means we're looking where it crosses the x-axis. And in between 0 and 2 pi, we can see that happens in 3 different places. At 0, at pi, and at 2 pi. Again, plugging any one of those 3 in would give us tan x equals 0. And since the overall equation is cos x times tan x, if at any point cos x equals 0 or tan x equals 0, the overall equation is going to equal 0. That means that any one of these 5 solutions that I've identified are going to be a solution to the overall equation. So we should just group them all together then. And I would write them in order from least to greatest usually. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. So it's the collection of all the solutions. Sometimes we have to rearrange, sometimes we have to factor, and so that's where we can draw upon skills from previous math courses. In this case, being quadratic, you probably want to think back to the work you've done with quadratics in the past, which would involve factoring things. So I'm going to bring that sine x over to the left, and then I'm going to common factor sine x out, because I can take a sine x out of each term. There's 2 terms. If I take sine squared x, remember that sine squared x simply equals sine x times sine x. That's what sine squared x means. So I could factor out one of those sine x's, and I'd still have a sine x left. And if I factor sine x away from this second term, the minus sine x, then that just leaves me with 1. And you can check that by expanding it back out. If I multiply both those terms in the brackets by sine x, I'd get back to what I started with. But anyway, what I can do, then I guess all I need to do is factor these ones. I don't need to go any farther. But if I was going to solve these ones, then I could set sine x equal to 0. I could set sine x minus 1 equal to 0 and solve those. For one like this, I could, again, bring the 1 over to the left side, again, because it's a quadratic, so I want to put it in standard quadratic form, where all the terms are on one side and then I factor. Now, I don't know if you recognize this or not, but this is actually a difference of squares. This is a perfect square. This is a perfect square. The square root of 4 cos squared x would just be, well, the square root of 4 is 2, and the square root of cos squared x is just cos x. So I'm going to have my two brackets for my difference of squares, and in the front part of each of those brackets I have 2 cos x, and then the square root of 1 is just 1. And you remember, for difference of squares you have plus 1 and minus 1. So that's my factored form of the difference of squares. Again, I could get back to what I started with just by doing FOIL on that. And that's all we're asked to do for that question. Now let's put it together where we have to simplify and factor and go all the way as far as solving it goes. So we have 3 sine squared x minus 2 equals cos x tan x. The first thing that you might notice about this is we got a lot of different types of trig ratios going on. We got sine, cos, and tan, which is problematic because with this quadratic part here on the left, I need to be able to factor something. So the ideal way to factor it would be to see if I can get it all down to one trig ratio that could then be common factored or some other type of factoring done on it. Whenever we see tan x in a situation that involves simplification of an equation, a great technique that you may remember is to change it from tan x into sine x over cos x, and then see if you can simplify that way. So tan x is the same as sine x over cos x. And that's great because then I can cancel the cos x's out, and I'm just left with sine x on the right. So now the only terms I've got left are all sine x, which I should be able to work with. I'll bring the sine x from the right over to the left-hand side. So I'm going to subtract sine x. I'll insert it in the middle here so that we're going from highest power, the sine squared x, down to sine x, down to minus 2. But all I've done is rearrange, bring that sine x over to the left-hand side. And again, hopefully you recognize that this is just quadratic. This is no different from something like, I'll erase this in a second, but this is no different from, say, 3m squared minus m minus 2. Right? This is just a quadratic, but instead of m, I've got a sine x. But I can factor it the exact same way. So I would try to find two things that are going to multiply. Well, actually, this is one that you could either use decomposition or trial and error on. So I like trial and error. I'll just do my rough work over on the side, and if you recognize this way of doing it, that's great. If not, then do your own way to factor this. But I want two things that are going to multiply to give 3 sine x squared. So I need a 3 sine x times just a 1 sine x. And as far as the 2 goes, I need to have a 2 and a 1, trying to multiply. See, these two multiply to give this term, and I need two numbers that are going to multiply to give negative 2. And so if I try 2 and 1 like that, then when I multiply diagonally to check my middle term, that would give me 3 sine x and 2 sine x. And I need a negative sine x out of that. So if I make this a negative 3 sine x, then I'd be able to get a negative sine x by combining those two. In order to make that a negative 3 sine x, that means I'd have to stick a minus sign in front of that 1 and make it a negative 1. But now everything works out. And then I read horizontally from my two factors. So 3 sine x plus 2 and sine x minus 1 would be the factors. So however you factor it, doesn't have to be that way, it doesn't matter to me, but you do have to be able to factor a quadratic, and this is just a quadratic that looks more complicated because the trig stuck in there. Once it's factored, we set each factor equal to 0. So 3 sine x plus 2 equals 0. If I subtract 2 from each side, and then divide each side by 3, I get sine x equals negative 2 over 3, right? So I'm going to need to then solve this like in the method we did on the last lesson, where I then find a related acute angle beta that's going to give me a sine x of positive 2 over 3, ignoring the negative. But before I get to that, let's just factor or solve this other linear one here. Sine x minus 1 equals 0, therefore sine x equals 1. That one's a bit easier because sine x equals 1, there's a couple ways of thinking about it, but the easiest one, I think, is just to picture the graph. Let's quickly sketch it again. Sine looks like this. The maximum is 1, so sine x is going to equal 1 in only one place, and that's, if you recall, at pi over 2, since the full cycle is 2 pi, this would be pi. So just thinking about our sine graph gives me a solution of pi over 2. Let's just call that one x1, because that is going to be one of our solutions, and we can't really do anything else with that part, so we're already half done, let's say. This other one's a bit more troublesome, though, because, well, I could look at the graph, and, you know, if I was to try to find sine x equals negative 2/3 on the graph, that would be somewhere around here. So it looks like there's going to be a couple solutions, but negative 2/3 is one of those weird in between. It's not a special triangle. I can't use special triangles, in fact, to do this one. So I'm going to go back to the technique that I had from yesterday, where I'm going to draw it on the Cartesian plane. So, cast rule. I guess maybe I'm getting a bit ahead of myself here. What I want to do, let's move this down a bit, because I think I'm going to want a bit more space now that I think about it. So, as I was mentioning a minute ago, we should get the related acute angle always. So I'm going to say sine beta equals positive 2 over 3, and then I'll find that related acute angle and I'll stick it onto the Cartesian plane that I just moved. But since this is not a special triangle, I can use a calculator for this. So I would just rearrange this one. Beta equals sine inverse of 2 over 3. And, so on the calculator, 2 divided by 3, 0.6 repeating, second sine, that's already got the second function chosen, so over on the left you'll see sine with a negative 1, which I'm just about to tap, and I got 0.73 if I round that. And I'm in radians, yes, so just double check. So beta equals 0.73. Remember, in radians, we don't have units, it's not degrees, it's just about 3/4 of 1 radian. Again, to give you a reference point, remember 1 radian is about equal to 57 degrees, or even we can call it about 60 degrees. So 3/4 of 1 radian is about 45 degrees. But not quite, not exactly. So it's about 45 degrees, or 0.73 radians, and remember it's negative. This negative sign does matter. I didn't drop it permanently, I just dropped it when I was doing beta. But it matters because it tells me which quadrants to put that 0.73 angle in. And being a negative sign, sine is positive in quadrants 1 and 2, so it's going to be negative in quadrants 3 and quadrant 4. And so we then have beta equals 0.73, that's our angle there, in both of these quadrants here. But we always measure from the positive x-axis, so we'll start here and come around to here. So if we call this one x2, since we already had an x1, as you can see just at the top of the screen, we know that x2 is going to equal pi, because from here to here, half a circle is pi plus 0.3, and therefore x2 is going to be pi plus 0.73. Pi plus 0.73 equals 3.87. That is another answer, another solution. And finally, let's use a different color for my pen. I have to go all the way around to here, starting again at the positive x-axis. That's going to be x3. And in this case, it's almost at 2 pi, right? Going from here all the way around is 2 pi, but I have to back up a little, and I have to back up to where that terminal arm is. So x3 is going to equal 2 pi, but not quite. It's going to be 2 pi minus 0.73. .55. And that would be my final solution. I know that there's no more solutions because, again, we're looking on the interval from 0 to 2 pi. So one rotation around, we saw that there's 2 solutions in that one rotation I just illustrated there. And as far as the other part goes, there's one cycle sketched on the sine graph. So there's 5 solutions circled in red that you can see there. So to sum up, solving quadratic trig equations is exactly the same as solving linear trig equations once you've factored the quadratic and then set each factor equal to 0.